The topic today is the central limit theorem for proportions. This is presentation 7.7. We want to acknowledge the development team of Brad Spencer and Amanda. We're going to illustrate the proceedings with the idea of a population of birds with a certain infection rate, in this case 20%. We suggest that this forms a binomial random variable which consists of n trials or n selections from the population of birds. There are two outcomes, either the bird is infected or not, and the probability of success or infected bird is 20%. And we're going to take samples of 64 birds from the population, and if we get 14 successes or birds infected, we're suggesting that proportion is 21.9%. We list them here. If we repeat that and get 12 successes, then the result is 12 over 64 or 18.8%. And we continue this for 20 samples and come up with 20 sample proportions. And you see some of those coming up on the screen here now. We want to suggest to you that these sample proportions follow a normal distribution. And you see them coming up here now. These red dots denote proportions, and they will cluster around 20%. As you can see here, they do tend to approximate 20%. Now the standard deviation is given by P1 minus P over n, where P is the probability of success, or 20%. That turns out to be 0.05, and that effectively gives the plus or minus 0.05 from the center, or 20%, with 68% probability. Now we've just gone to another screen here. We want to look at a 95% interval, and as we said previously, 95% associated with plus or minus 1.96 z-score, and we multiply your critical value, or 1.96, times your standard error to give us the margin of error, which turns out to be given here, 0.098. And we're suggesting that if we do have a sample proportion, then we have these red dots here denoting 19 out of 20 of these proportions will fall between these two red lines. One on average will fall outside, and if we take the margin of error and add and subtract from each of those sample proportions, we get a confidence interval. And what's coming up on the screen here now, so if we find that, if we take one of those, for example, p hat is 24.7%, we simply compute the confidence interval by taking your 24.7% plus or minus your margin of error, giving you a confidence interval for the population proportion between 14.9 and 34.5%. And we're saying here that there's 95% chance that this interval, given above here, is 95% chance that that interval will capture the true population proportion. Now we're going to look at another example. We're looking at a flu control with imbecile, and we're looking at a random sample of 524 flu patients treated with imbecile. 84 experienced nausea, adverse reaction. We need to compute a 95% confidence interval for the population proportion P, and we're saying that the sample proportions will cluster around some unknown proportion P, that's the population proportion. A point estimate of that is x over n, 84 over 524, 16%. And the standard error in this estimate is given by this formulation here, where we use p hat as an estimate of P in this formulation here, giving us plus or minus 1.6%. That's your standard error. And we see that is your 68% confidence interval about the unknown proportion P. Now looking at a 95% confidence interval, z-score is plus or minus 1.96 times your standard error, giving you a margin of error, coming on the screen here now, plus or minus 0.031, and that tells us how close we are to the population proportion with 95% confidence. Now on to the confidence interval. We have here these red lines which denote a 95% confidence interval about the true proportion P, and we're saying somewhere there, 19 times out of 20, our sample proportion P will fall between those two red lines. So if P is equal to 0.16, which we get here from our point estimate above, then we can compute the confidence interval plus or minus 1.96 times your standard error. And this gives rise to your estimate plus or minus your margin of error. And that interval becomes, coming on screen here now, 12.9% to 19.1%. And we can be 95% confident that this interval will capture the true proportion P. Suppose that the rate of nausea amongst patients given the placebo is 6%. On this basis, should one be concerned about the rate of nausea experienced with this imbecile, labeled here Tamiflu? And the answer is yes. This constitutes sufficient evidence to suggest that the rate of nausea for the use of imbecile is significantly above normal. Well, that's the end of presentation 7.7. We ask you to review it once again and continue to presentation 7.8.